All right, so here we are with the notes for the review on the arithmetic series and sums. Hopefully this will go well. We'll find out, I guess. What is an arithmetic sequence? It is a sequence that moves from term to term by addition or subtraction, because that's what arithmetic is, of a common term, common difference. And we call that D. That's what an arithmetic sequence is. There's two ways of writing these. We have what's called an explicit rule. It says that the nth term is the first term, which we call a sub 1, plus parentheses n minus 1 times d, where a sub 1 is the first term and d is the common difference. All right, then we have the recursive rule. The recursive rule is where you have to just, well, the explicit rule, if you plug a number in, you get something back. The recursive rule is where you have to kind of like, all right, I know that I'm going to add 2. What's the 10th term? So you add 2 10 times. That's what a recursive rule is. Recursive rule is a piecewise function. You are the first term if you're located at position 1, and you're the previous term plus the difference if you're at a term greater than 1. Anywho, moving forward, determine if the series is arithmetic. If so, write a recursive rule for it. So here I noticed that the difference is 7, and I noticed again that 12 minus 5 is also 7, and 19 minus 12 is also 7. So yes, there is a common difference. We're always adding 7 as we move right. If so, write a recursive rule for it. So the nth term will be the first term if the term number is 1, and it will be the previous term. That's the previous term. Maybe you remember doing that, maybe you don't. Plus 7 if n is greater than 1. Moving on to the next one, we go from 3 to 8, which is adding 5, but then we go from 8 to 14, which is adding 6, and then we go from 14 to 21, which is adding 7. No, there is no common difference. So we're not even going to write a rule. An explicit rule for an arithmetic sequence is given. Write a recursive rule. All right, so we'll recap here. We need some stuff. We need to know the first term. And what we need to know is this common difference. So let's find the first term by plugging in a 1. And 16 minus 1 is 11. So when I write my rule, there'll be an 11. And I know what the common difference is by looking at this thing, but I have more experience than y'all. I'm going to find the next term by plugging in a 2. And then we get a 27. The difference is 16. See it right there? There's your difference. So I'm going to be the previous term called a sub 1 n minus 1, add 16 if n is greater than 1. That's all you do. These aren't too bad. Recursive rule is given, write the explicit rule. That should say a sub n minus 1. I still haven't corrected this. All right, so I'm supposed to write the explicit rule. The explicit form is that I'm going to be the nth term. The nth term is the first term plus parentheses n minus 1 times the common difference d. And I'm just going to plug some stuff in. I know from the previous examples that this is the first term and this is the difference. So I just need to plug those things in and go to town with it. So the nth term is going to be negative 12 plus parentheses n minus 1 times a difference of negative 6. And we've been Doing lots of algebra for a long time. I mean, we know the distributive property, kids. Negative 6 times n is negative 6n. Negative 6 times negative 1 is plus 6. We've been combining like terms for years as well. Negative 6n leads, and then we have negative 12 plus 6, which is negative 6. You wanted to make these things kind of look like mx plus b, because these are lines, is what they are. All arithmetic sequences are nothing more than lines. They have a slope-intercept, they have a slope, they have a y-intercept, they have all that good stuff. What's up next? Fill in the gaps in this arithmetic sequence, negative 3, 5 spaces all the way to a 12. So this one is not something that most people can do in their head. I can look at it and I can tell you it's a fractional difference. It's probably, I hadn't seen this example before, but it's probably around 5/3, 5/2. It's something like that. But, you know, there's a way to do it without adding left and right, without thinking about it. We're going to find the difference between the first and the last. All right. So the difference is 12 minus a negative 3, which is 15. And what we're going to have to do is we're going to have to add something 1, 2, 3, 4, 5, 6 times. So since I have to add same thing 6 times to get to 12, I'm just going to do 15 over 6. Then I'm going to reduce the fraction. So 15 over 6, they're both divisible by 3, is 5/2. And this will work. It will. If I did it right. All right, so negative 3 is a negative 6 over 2. And if you add 5/2, you're at negative 1/2. And, you know, then we're at negative 1/2. And we're going to add 5/2, right? That's going to be 4/2, which is 2. And then we're at 4/2, and we're going to add 5/2, and that's going to give us 9/2. And then we're at 9/2, and we're going to add 5/2, and that's going to give us 14/2, which is 7. And now we're going to add another 5/2, and that's going to give us 19/2. So we're at 19/2, and we add 5/2, and now we're at 24/2, which is 12. So it'd be nice if you could always just rely on brute brain power to figure these out, but sometimes you just need an algorithm to do it. And there's the algorithm. Let's see, 3 stages of a pattern are shown below using matchsticks. Each stage requires a certain number of matchsticks. If we keep up the pattern, how many figures are required to make the figure in stage 34? What stage would require 220 matchsticks? So let's see what we got here. We got 4, 7, right? 1, 2, 3, 4, 5, 6, 7, and then 10. We have a difference of 3. We're adding 3 as we move left to right. So what we're going to do is we're going to write the general rule, and we're going to use explicit forms, that a sub n is the first term plus n minus 1 times the difference of 3. And I don't know why I didn't put a 4 there, but whatever. I'll have 3n minus 3 plus that 4, so 3n plus 1. I can now find any particular term. So like part A says, how many matchsticks required to make the figure in stage 34? Well, I'm going to find a sub 34 by plugging in a 34, and then I'm going to do some math, you know. 3 30s is 90, 3 4s is 12, that's 102, add 1, 103. 103 matchsticks will make figure 34. What stage requires 220? Well, this is an output. This is a goal, okay? That's going to be on the other side. We're trying to figure out what stage it is. So 220 equals that form right there, 3n plus 1. Subtract 1, you get 219. And what's that going to be? That is going to be 73. So 73rd stage. Require 220 matchsticks. Easy peasy, lemon squeezy. Joe Robin walks 2/10 of a mile the first day, 5/10 the second day, and 8/10 the third day. So his, her, their, they, them, whoever they are, their common difference is 3/10 of a mile. 2/10 plus 3/10 is 5/10 plus 3/10 is 8/10, and so forth. If this pattern continues, how many miles will she walk the 30th day? We could do this recursively. We could add 3/10 for a long, long time. I just don't have time for that. So we're going to write the explicit rule, because explicit means straight and to the point. It says that the nth term is the first term plus n minus 1 times the common difference. So the first term is 2/10 of a mile, and the common difference was 3/10 of a mile. All right, easy peasy lemon squeezy, kids. Let's distribute that 3/10. So plus 3/10 of n minus 3/10, distributive property. You don't need a calculator for everything. And then let's combine like terms. So the nth term is 3/10 of n minus 1 singular tenth. Now I want to know how many miles they are going to walk on the 30th day. So I'm going to find a of 30 by plugging in a 30. It's a lot, not really. Let's see here. 3/10 of 30. What could that be? I feel like it's 9. So we have 9 minus 0.1, which is 8.9 miles. How many miles Joe Robin's walking on the 30th day at the end of the month? It's a pretty good walk. Find the sum of Joe Robin's 30 days of walking. So I don't know if you remember how we did this, but it was Gauss who came up with this. Gauss was tasked with finding the sum of the numbers 1 through 100, and he came up with a pattern. Plus 2, plus 3. This has nothing to do with this question. Plus ... 97 plus 98 plus 99 plus 100. And he noticed that the outside terms were always 101. So he came up, we recognized a pattern, and I guess later he formalized it. But the sum of n terms is the number of things you have divided by 2, because there would be 50 pairings of 101 times the first plus the last. That's what this one is, the last. So find the sum of Joe Robin's 30 days of walking. So we know that the first day, according to the text, I believe it was 2/10. And the last day was 8.9. And we're just going to plug things in. This is n. So the sum of 30 days is 30 over 2 times 0.2 plus 8.9. 30 over 2 being 15, this being 9.1. 15 nines is 145 plus 1.5, 146.5. Double check that real quick. You got 90 and 45, 135. That's not right. That's why I double check sometimes. 136.5 miles. Moving forward, Ellie thought that I made a mistake. Find the sum of the first 100 odd numbers. Mistake here. So we talk about your odd numbers. 1, 3, 5, 7, so 9. You have sigma, which you haven't seen in a while. 11, ... Your odd numbers. That is the Greek letter. There should be 50 of them. There should be. So you're going to find the sum of 50 things. And that's going to be done by taking. Now I know the number of things there are divided by 2. It looks kind of like y, and then the first plus the last. Now, the first we're going to find some terms. The last is 99. This is the sum of the 100th. So we got a 50 over 2, which is 25 times 100, which is 2,500. So when we do our little formula summation, which we just talked about, find the sum of the positive terms in the arithmetic sequence 85, 78, 71, 250th term. So it looks like we're losing 7. Now, to find the 100th term, I'm just going to write the sequence out because it's not that big. So 71 minus 100 is what, 64? And to find the 250th term, you plug in 250. So So 650 minus 250.
43,
which
take away
is
7 is 36.
I don't know why I'm writing 650.
I'm cautious
600
about doing
minus
this 'cause
250, which is 300.
good as I am at math,
Granted,
there's
I
a
just want
chance
to
I'll
keep
make a
messing this thing
mistake.
up.
But
All right,
it was
so
worth
here's
the
the
risk.
question: is how many things
All right, then
are
we
there?
got 22.
A lot of kids would say 250, which obviously isn't right because it's the sum of 100 to the 250th term.
And we stop because we
but
only
n
want
is
positive terms,
always
right?
high.
So how many things do we have? We have
Minus
3,
the low.
4, 5, 6,
Plus
7, 8,
1.
9, 10, 11,
That's the
12,
kicker, you gotta add
13
one.
terms. We're finding
So the big
sum
number
of
up top's
13
250,
things.
the little number's
It's going to be
100.
a 13
and you
over
add
2.
one.
The first
250
term was
minus 100 is
85.
150. You add 1, you
The
get
last term was
151 terms.
81.
The first term that I care about
So
is
what we have,
500.
we have 86.
The last term that I
That's
care about is
43.
350.
You cut it in half.
So these numbers are going to be a little too
1343
big for me to do in my
430,
head right now.
120
Plus I'm in a
makes
hurry.
550. Should be
So let's see what the
559. Let's check
TI-84
me.
tells me. It's early in the morning. I haven't quite woke up. The safe way would be to go to math, num n over d, but I'm just going to use parentheses. So
If I'm
151
wrong,
over 2
I'm
on
wrong.
the outside,
I'm not.
500 plus 350 on the
Second
inside.
term of
If you don't know, that's 850. TI-84, don't judge. It's nice like that. Should, but whatever. 64,175. That's the correct summation. 64,175. And now to see if I can ace this over the mistake, so none of you see the mistake. But thank you to Ellie. So bummer, fixing that mistake trashed the rest of the video after that. So let's see if this can fix it, or if I have to redo the whole thing. Find the sum of the first 100 odd numbers. So it's going to start at 1, then 3, then 5, and stop at 99. There should be 50 of them, I think. So we're going to use the same formula as we had before. The sum of n things is n over 2 times first plus last. And the first guy is 1, and the last guy is 99. There are 50 items, so it's 50 over 2. We're finding the sum of 50 things. We'll have 25 times 1 plus 99, which is 100, and we'll get 2,500. Find the sum of the positive terms of the arithmetic sequence 85, 78, 71. Now this is kind of a small sequence. I could use a formula to figure out the last term, but I'm just going to keep counting down. So we're taking away 7. 71 minus 7 is 64, minus 7 is 57, minus 7 is 50, minus 7 is 43, minus 7 is 36, minus 7 is 29, 22, 15, 8, 1. And the next guy would be negative 6, and we don't want him because he ain't positive. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 13 things. Let's do that again. 3, 6, 7, 10, 13. So there are 13 items. We're going to find the sum of 13 things. She shall be 13 over 2. First term is 85. Last term is 1. So this is the sum of 13 things. We'll have an 86. Half of 86 is 43. That'd be 430 plus 120 plus 9 should be 559. So I think that's it. Yeah, the rest of it's you try. So let's try and paste this over and see if maybe I can salvage my work.